Today we are going to discuss the paired t-test or the t-test for dependent means, and in the previous lecture we discussed the unpaired t-test or the t-test for independent means. So today we are going to see that what is meant by the paired t-test and how this test is executed. So this test is also known as the matched samples t-test. Why this is known as the matched samples t-test? Because the samples, they are matched. The observations are matched with each other. And this is also known as the paired samples t-test. Why this is known as the paired samples t-test? Because the observations in the two groups, they are paired, right? So all the observations that we have, they are present in a pair of two. And this is also known as the dependent means t-test, because the observations in each of the pairs that we have, these observations are dependent on each other. So that is why it is known as the dependent means t-test. Then it is also known as the repeated measures t-test. Now why this is known as the repeated measures t-test? Because the observations are they are repeated, right? The paired observations that we have, they are the repeated measures, which means that the same variable, it is measured twice from the same sample unit. So that is why these are paired, or these are dependent on each other. So these are the different names for this test, the paired t-test. Now this test is commonly used to test the statistical difference between two time points. For example, we have cholesterol levels before and after the use of a medicine. So in this case, we are talking about an intervention study in which we have some individuals who suffer probably from the high cholesterol level, and we want to try a new drug on those patients. So we are going to take their cholesterol levels before the start of the treatment, and then we are going to take their cholesterol levels after the application of the medicine, after a few weeks or after a few months. So it means that we are going to take the observations in pairs from each individual. So let's suppose we have 5 individuals, so we are going to take 5 pairs of observations. The number of observations are 10, but the pairs are 5. So these are the paired observations, and the observations in each of the pair are dependent on each other because they're taken from the same individual. And these are the repeated measures because the same variable is measured twice from each sample unit. And then this test is also used to test the statistical difference between two conditions. For example, blood pressure in resting condition and fever. And again, in this case, if we have individuals and we want to see that if there is a difference in their blood pressure when they are in resting healthy condition or when they are in fever. So we are going to measure their blood pressure in the resting healthy condition, and then we are going to take the readings of their blood pressure when they are suffering from high fever. And if you want to know that if there is a significant difference in the mean values of blood pressure in both of the conditions, then we can apply the paired t-test. Again, these are the paired observations which are taken from the same group of individuals. And these are repeated observations because they are taken at two different times, under two different conditions. And then the paired t-test is also applicable when we want to know the statistical difference between two sides or halves of the same unit. So in this case, we are not taking the observations under two different conditions. We are not taking the observations at two different time points. Rather, we are taking the observation at the same point, but this time we are taking observations from two halves of the same individual. So for example, if we are going to take measurements for the variable or for the object which is present twice on each subject, right? For example, the human beings, we are symmetrical for the ears, so we have one ear on each side of our body. So if we want to see that is there a statistical difference in the degree of hearing impairment between our group of individuals between the two ears. So for that purpose, we are going to use the paired t-test. So in this case, we are again taking the repeated measures because we are taking the same observation 2 times from the same individual, right? And this is also the dependent mean because the individual is same and we are taking paired observations. We are taking 2 observations from the same individual. So these are the general conditions in which we can apply the paired t-test. Now let's see what are the requirements of the paired t-test. The first requirement, as its name indicates, is that the two sets of scores or two sets of observations, they are paired or matched in some way. So the two observations, they should not be independent of each other, rather they should be paired. And the data is normally distributed, that the observations, they follow a normal distribution pattern. And the scale of measurement should be interval or ratio. It means that this kind of t-test can be applied on the continuous variable that is measured on the interval or the ratio scale. And this paired t-test is not appropriate for analysis of unpaired data. So if you have two groups and you want to compare their mean values, and if the observations, they are not paired, then you can apply the t-test for independent means. So you cannot use the paired t-test for that purpose. And it is not appropriate for the analysis of comparisons between more than two units or groups. So it means that you cannot apply the paired t-test when you have more than two groups. So it can be applied only on the two groups. And same is true for the independent samples t-test, that the independent samples t-test can also be performed only on two groups. So it cannot be performed on more than two groups. And it is also not appropriate for the analysis of a continuous variable that is not normally distributed. So it should follow a normal distribution pattern. And similarly, it is not appropriate for the analysis of the outcome which is ordinal or ranked. So it is not good for the observations which are measured on the ordinal or ranked scale or on the nominal scale. So it is good only for the observations which are measured on the interval or the ratio scale. So this is where we can or we cannot apply the paired t-test. Now, how to execute the paired t-test. So we are going to take the example of the masses of a group of birds that was measured in August and September. So here are 10 birds, and these observations, as you can see, that these are paired observations. These are repeated measures because the same variable is being measured twice on the same birds. So these are the observations, and then you can see the mean values. So the mean mass of birds weight in August is 11.47 grams, and the mean mass of birds weight in September is 12.35 grams. So apparently we can see that there is a difference in the mean values. And although that difference doesn't look like a huge difference, but still we have to see that whether this difference is significant or no. So our question is there a significant difference in the mean mass of birds between August and September, right? So this is our question. Now, the null hypothesis to test that question is the mean mass of birds is same between August and September samples. So this is null hypothesis, we are assuming no difference. Then the alternate hypothesis, the two-tailed alternate hypothesis, is the mean mass of birds is different between August and September samples. So you have to apply a t-test of repeated measures or dependent means, and this is the formula for the t-test for repeated measures or the paired means. So here you can see that you have the n, which is the number of groups or the number of the sampling units, and you can see d. So what is d? D is the difference between two observations, right? So because this is the paired data, so we have to take difference of each one of these pairs, and that difference is d. Now you can see that there are three factors in the formula. This is summation d, and then it is summation d square, and then this is summation d whole square. So all these three things are different. Summation d means that you take the difference of each pair individually, and then you take the sum of all the individual d values. So that will be your summation d. So summation d square is that you take the differences, you calculate the d value for each pair, and then you take the square of each d value, So if you have 10 d values, you take the square of each one of these 10 values, and then you take the sum of these squared d values. And summation d whole square means that you take the sum of the individual values, which is the summation d, sum of the difference between the individual pairs, which is summation d, and then you take the square of that value. Now let's see that how it is done. So this is the table for the calculation of the paired t-test. So you can see that we have in the first column the masses of birds weighed in August, and then in the second column we have masses of birds weighed in September, and then we have the third column, which is the d difference between each pair of observations. So the first pair of observations is 10.3 and 12.2. So the difference is 12.2 minus 10.3, and the answer is 1.9. And then it is 12.1 minus 11.4, so the answer is 0.7. And then you have 13.1 minus 10.9, and the difference is 2.2. And then you have 11.9 minus 12, so the difference is minus 0.1. And then you have 12 minus 10, and the difference is 2. Then you have 12.9 minus 11.9, the difference is plus 1. Then you have 11.4 minus 12.2, and the difference is minus 0.2. And then you have 13.5 minus 11.7, and the difference is plus 1.8. And then you have 12.3 minus 12, and the difference is 0.3. So when you take the sum of this column, the sum is 8.8. So summation d is 8.8. Now the reason that these plus and minus signs are shown here, because when you're going to take the sum of this column, this is going to matter. So because we have the two-tailed alternate hypothesis, so it doesn't matter that if we subtract the value of first sample by the second sample, or the value of second sample by the first sample. Only their signs are going to be different, but their summation d is going to be the same, right? So you can try this at your home, and you can try subtracting 12.2 from 10, and then so on, right? So you can do it either way, because we are assuming the two-tailed difference. So unless and until we have the one-tailed hypothesis, we can subtract either way. So in the next column we have d square. So d square is the square of the independent square of each of these d values. So 3.61 is the square of 1.9, 0.49 is the square of 0.7, 4.84 is the square of 2.2, and then 0.01 is the square of 0.1, then 4 is the square of 2, 1 is the square of plus 1, 0.64 is the square of 0.8, and 0.04 is the square of 0.2, 3.24 is the square of 1.8, and 0.09 is the square of 3. Now we take the sum of these square values, and the summation d square is 17.96. So now you see that these two values are different, right? So summation d is different and summation d square is different. Now we move on to the calculations. Next calculation. So here we are. So we have the formula. Now we put in the values. So summation d is 8.8, and n is 10, and summation d square is 17.96. Now the third factor, which is the summation d whole square, is actually the square of summation d. So what is our summation d? Summation d is 8.8. So we take the square of this value, and that will be summation d whole square. Then we have 10 minus 1, and 10 is our number of pairs. So here we have 10 multiplied by 17.96, and the answer is 179.6, and we take the square of 8.8, and the square of 8.8 is 77.4. Then we have 9, which is the difference of 10 and 1. So I have pasted the same step over here, and now we do the further calculation. So we have 179.6 minus 77.44, and the answer is 102.16. Now we are going to divide 102.16 by 9, and the answer is 11.3511. In the next step, we are going to take the square root of 11.3511, and the answer is 3.3691. So now we divide 8.8 by 3.3691, and the answer is 2.612, which is our test statistic, which is the value of t that we had to calculate. And the degree of freedom for the paired t-test is n minus 1, which in this case is 10 minus 1 equal to 9. So here again we have a difference from the independent samples t-test. So in that case, the degree of freedom is n1 plus n2 minus 2, and n1 is the number of observations in first sample and n2 is the number of observations in the second sample. But in this case, because we have the paired data, so n refers to the number of sampling units or the number of paired observations. So in this case we have 20 observations, but these observations are 10 pairs actually. So that is why we have taken 10 as n. Now we have our calculated value with us, so this is time to consult the t-distribution table, and the degree of freedom is 9, and the first level of critical probability is 0.05, and this is the tabled value. So the table value is 2.262, which is less than the calculated value. So therefore, what we are going to do with the null hypothesis, we are going to reject the null hypothesis in favor of alternative hypothesis, and the significance level is significant. Now we want to see that if it is significant at the next level of significance as well. So the next level of significance is 0.01, and the table value is 3.250. So in this case we can see that our result is not highly significant. So it is not significant at the probability of 0.01. So there is no point in checking for the next significance level of 99.99% or probability of 0.001. So now it is time to report the results. So our t-value is 2.612, our degree of freedom is 9, and the table value at probability 0.05 is 2.262, which is less than the calculated value. So the calculated value is greater than the tabled value at probability 0.05, and therefore we can say that the mean mass of birds is significantly different between August and September samples. T 2.612, probability less than 0.05. So this is our first example for today. And now we have the second example for the paired t-test, and this is a group of patients suffering from high total serum cholesterol level, and this is measured in milligrams per deciliter, and they were treated with a new cholesterol lowering drug. So find out if the new drug significantly alters the total serum cholesterol levels. So this is the example that we have. Now the question is, does the new drug alters the total serum cholesterol levels? So this is our research question that we have to check. These are the observations that we have. So you can see that the mean serum cholesterol level before the use of drug is 283.8, and the mean serum cholesterol level after the treatment with drug is 278.2 milligrams per deciliter. So apparently we can see that there is a difference in the serum cholesterol level. So now it is time to see that whether this difference is significant or no. And for that purpose we have to state our hypothesis. So our null hypothesis is the new drug does not alter the total serum cholesterol levels. And the alternate hypothesis is new drug alters the total serum cholesterol levels. And we have to apply the t-test of repeated measures or dependent means, because we are taking the repeated measures from the same individuals under two different conditions, before and after the intervention. And this is our formula for t. So here we are with the table for the calculation of summation d and summation d square values. So we can see that this is 256 minus 261, and the answer is minus 5 for the first patient. Then we have 264 minus 262, and the answer is 2. And then we have 278 minus 271, and the answer is 7. And then we have 284 minus 272, and the answer is 12. And then it is 285 minus 278, the answer is 7. And then we have 289 minus 284, so this is the answer is 5. And then we have 291 minus 285, and the answer is 6. And then we have 294 minus 288, which is equal to 6. And then we have 298 minus 290, and the answer is 8. And then we have 299 minus 291, and the answer is also 8. So in this case, you can see that there is actually a decrease in the serum cholesterol levels, except for the first patient. So now we are going to take the squares of these individual differences. So 5 square is 25, and the square of 2 is 4, and the square of 7 is 49, square of 12 is 144, the square of 7 is 49, the square of 5 is 25, and the square of 6 for the next two values is 36 each, and the square of 8 for the next two values is 64 for each pair. Then we take the sum of the column number 1, and the summation d is 56, and then we take the sum of the second column, and the summation d square is 496. So now we have the values of d and d squares. So it's time to put in the values into the formula. So we have 56, which is summation d, and then we have 10, which is the number of pairs, and then we have 496, which is the summation of individual differences and their square values. And then we have 56, which is the square value of the sum of the differences. Then we have 10 minus 1. So we have 56, and we have 4960 and 3136, which is the square of 56, and we have 9, which is 10 minus 1. And now continuing with the same step, we have 1824, which is 4960 minus 3136. Now we are going to divide 1824 by 9, and the answer is 202.6667. Right? Now we take the square of the 202.667, and the answer is 14.2361. Now we are going to divide 56 by 14.2361, and the answer is 3.9337. So this is the t-value that we have calculated. And what is our degree of freedom? So in this example, we have the degree of freedom as 9. Now it is time to consult the t-distribution table. The degree of freedom is 9, and the level of critical probability is 0.05, and the table value is 2.262. So we can see that our calculated value is greater than this value, so we are going to reject null hypothesis in favor of alternate hypothesis, and our significance level at this point is significant, which is 95%. Then we want to see that if this result is significant at the next level as well. So the next level is 0.01, and the table value is 3.250, and this value is also less than the calculated value, so which means that our results are highly significant. So the significance level of our results is 99% as well. Now we wish to see the next level of critical probability, which is 0.001, and the table value is 4.8781. But in this case, our table value is greater, so we can say that our results are not very highly significant. And now it is time to report the results. So t is 3.9337, degree of freedom is 9. The table value at probability 0.05 is 2.262, which is less than the calculated value. Then the table value at probability 0.01 is 3.25, which is also less than the calculated value. And the table value at 0.001 is 4.78, which is greater than the calculated value. So what we are going to say is that the calculated value is greater than the table value at probability 0.01. Therefore, the result is new drug highly significantly alters the total serum cholesterol levels. T is 3.934 and the probability is less than 0.01. So this is the result that we got. And now it is time to see that how we can perform the paired t-test on Microsoft Excel. So for that purpose, first of all, you have to put your observations in an Excel sheet, and I have taken the example of the mass of birds measured in August and September. So I have these 10 pairs of observations in the Excel sheet. Now, what is the next step? We have to press the data analysis function button here, tab here, and we will have a pop-up window, and this window has got the list of all the statistical tests that can be performed under this function. So we scroll down to see the types of t-tests that we have. We have the t-test for the paired two samples for means, and the t-test for two samples assuming equal variances, and t-test for two samples assuming unequal variances. So what is our required t-test in this case? So our required t-test in this case is the t-test for the paired two sample for means. So now, after we have selected our test, we are going to press the OK button, and then we will have another window appearing, and this window has got the boxes for the input of values. So in the first box, we are going to place our cursor, and then we are going to select the range of the first set of observations. And then we are going to place the cursor in the second box, and we are going to select the observations from the second group. So we have our observations input into the box. Now it is time to press the output range button. So the output range button is used to select the cell sheet or the workbook for the output. So if we want to have our results into the same sheet, then we have to place the cursor here, and if we want to have the output appearing into a new sheet, then we have to select this button, and if we want to have our results into a new workbook, then we have to press this button, right? Now we want to have results into the same sheet, so we are going to place the cursor here, and we are going to select the cell in which we want to have the output. After we are done with this selection, we are going to press the OK button to get the output. So here is the output. Now we expand the output and see what we have got. So we have got the mean values, which is 11.47 for the first group and 12.35 for the second group. Then we have variances, which is 0.6534 for the first group and 0.3961 for the second group. Then we have the number of observations, because these are the matched or the paired samples, so therefore it has to be same in both of the groups. And then we have the Pearson correlation value, which is 0.0841 in this case. So this is the bivariate Pearson correlation coefficient for each pair of observations. So the correlation coefficient is another test. It is another statistical analysis that is used to see the correlation between the two sets of values. So in this case, this output is giving us the paired bivariate Pearson correlation coefficient values. So right now we are not interested into this result. Otherwise, this is used just to confirm that if you have got the significant result, then whether that result is significant at the level of each pair of observations as well or no. Right, and the next one is the hypothesized mean difference. So because we assumed null hypothesis and we tested against the null hypothesis, so our assumed or our hypothesized mean difference is none. It is 0. And our degree of freedom is 9, which is the number of pairs 10 minus 1. And then we have the test statistic, which is 2.612, and this is the probability for the one-tailed test, which is 0.014. So this is significant. If we assume the one-tailed test, then it is significant. And then we have the critical value for the one-tailed test, which is the table value. And then we have the probability for the two-tailed test. So we can see that this is also significant at the two-tailed hypothesis. So this is 0.0282. And then we have the critical value or the table value taken from the t-distribution table at probability 0.05 and degree of freedom 9. And this value is 2.262. So it means that our calculated value is greater than the table value. So we are going to reject the null hypothesis, and we are going to say that there is a significant difference in the mean values of the two groups or the two sets of observations. Now we can see that these are the same results as we had calculated. So we calculated 2.612, and here also we have the value 2.612. The degree of freedom is 9 in both of the cases. The table value is documented as 2.262. Obviously this is taken from the t-distribution table, so this has to be same. And our result is also same, and that the result is significant. So this is how we can execute the paired t-test or the t-test for the matched observations of the repeated measures t-test on Microsoft Excel. So this is it for today.